Now next is properties of normal subgroups. First, sufficient condition. Let G be a group and H be a subgroup of G such that index of H in G is 2. Then H is normal in G. Means G is a group, H is a subgroup of G, and index of H in G. This is 2. Then we will say that H is a normal subgroup of G. Second, if a group is abelian, then every subgroup of G is normal. But the converse need not be true. That is, if every subgroup of a group is normal, this need not imply that the group is abelian. For example, if I take G equal to Q8, quaternion group, its elements are plus minus 1, plus minus I, plus minus j, plus minus k. Subgroups of Q8 are H1 equal to 1, H2 1 comma minus 1, H3 1 comma minus 1 comma I comma minus I, H4 1 comma minus 1 comma j comma minus j, H5 1 comma minus 1 comma k comma minus k, and H6 is whole Q8. Every subgroup of Q8 is normal in Q8, but Q8 is non-abelian. So converse of this is not true. Every subgroup of a group is normal, then it does not imply that group is abelian. Next, normal subgroup is not a transitive property. That is, if H is a normal subgroup of G and K is a normal subgroup of H, then this need not imply that K is a normal subgroup of G. For example, D4, which contains rotations R0, R90, R180, R270 and reflections D, D dash, V and H. Now N is equals to R0, R180, V, H. Now as index of N in D4, that is D4 is to N. This is basically order of D4 upon order of N. Order of D4 is 8, order of N is 4, so 2. So whenever we have a subgroup N whose index in this group G is 2, then we will see that that subgroup is normal in G. Now if I take N dash, this is R0, H. Now index of N dash in N, that is, this is equal to order of N upon order of N dash. Order of N is 4, order of N dash is 2, so index is 2. This means that N dash is a normal subgroup of N, but N dash is not normal in D4. Next, intersection of two normal subgroups of a group G is again normal in G. Fifth, let G be a group N be a normal subgroup of G and H be a subgroup of G, then NH is a subgroup of G. Means G is a group, N is a normal subgroup of G, H is a subgroup of G, then NH is a subgroup of G. Next is factor groups. In general, if G is a group and H is a subgroup of G, then the set of left cosets of H in G does not form a group. Means if G is a group and H is a subgroup of G, then the set of left cosets of H in G means AH. This does not form a group. But if H is a normal subgroup of G, then the set of left cosets of H and G forms a group called the factor group. So definition: let G be a group and H be a normal subgroup of G. Define the set G by H. This is equal to GH such that G belongs to group G. And operation on G by H is defined as G1 into H, G2 into H. This is equal to G1, G2 into H. Then the set together with the operation defined above forms a group called the factor group. So wherever you will see this type of groups, they are factor groups or also known as quotient groups. Remarks: if the correspondence AH into BH is equals to ABH defines a group operation on the set of left cosets of H in G, then H is a normal subgroup of G. If this operation is defined on the left cosets of H in G, then H is a normal subgroup of G. Now some examples. First, group G is set of integers and subgroup is 4Z. So what will be G by H? Can you tell me what will be G by H?
It will be 0, 1, 2, 3.
It will be like this, na? 4Z, then 1 plus 4Z, 2 plus 4Z and 3 plus 4Z. And when I will write 4 plus 4Z, it will get automatically absorbed in 4Z. If I write 5 plus 4Z, it will get absorbed in this 1 plus 4Z. Okay. Note, this example shows that if a group is infinite, this need not imply that its factor group is also infinite. Here group G, set of integers is infinite, but we are getting factor group as finite. Because what is the order of factor group? 4 na? And order of group G is infinite. Second example, G is equals to S3. Identity 1 2 1 3 2 3 1 2 3 1 3 2. If I take a subgroup identity 1 2 3 1 3 2, so this is a normal subgroup of S3. Now what will be S3 by H? This will be XH such that X belongs to S3. So it will contain H 1 2 H, because 1 2 H 1 2 and H means I will take a member of this 1 2 3. Then it will be 1 goes to 2, 2 goes to 1, 2 goes to 3, 3 goes to 3, 3 goes to 1, 1 goes to 2. So it will be 2 3. And if I take 2 3 H means 2 3 into some element of H 1 3 2, then I will get 1 goes to 3, 3 goes to 2, 2 goes to 1, 1 goes to 1, 3 goes to 2, 2 goes to 3. It will be 1 2. So like this I will get the elements of this factor group. This means 1 2 H is equals to 2 3 H is equals to 1 3 H. अगर यहाँ पे एक बार मैं 2 3 H 1 3 2 लिया था, 1 3 2 की जगह अगर 1 2 3 लूँ ताकि पता चले कि सेम आ रहे हैं नहीं आ रहे. 1 goes to 2, 2 goes to 3, 1 goes to 2, 2 goes to 3, 3 goes to 1, 1 goes to 1. This is 1 3. 1 2 H 1 2 2 3 H. Okay.
इसको हमने सारे एलिमेंट से करना है.
हाँ फिर H के तो फिर लेने ही पड़ेंगे. H के तो ये दो लिए जाएंगे ना. आइडेंटिटी के साथ करेंगे तो सेम ही आएगा हर बार.
तो एवरी एलिमेंट को हमने 1 2 3 से भी करना है और 1 3 2 से भी करना है ना.
हाँ. Now next are some properties of the factor group. Let G be a finite group. If G is a finite group, then its factor group will also be finite. Then the factor group of G is also finite. If H is a normal subgroup of G, then order of G by H, this is index of G is to H. But the converse is not true. We have already discussed the example. If I take group G as Z and H as 4Z, then G by H, 4Z, 1 plus 4Z, 2 plus 4Z, 3 plus 4Z. So clearly factor group is finite, but group is infinite. Second, factor group of an abelian group is abelian. Means if group G is abelian, then G by H, this will also be abelian. Converse need not be true. For example, G is equals to S3, H is equals to identity 1, 2, 3, 1, 3, 2. Now order of G is 3 factorial 6, order of H is 3, so order of G by H, this will be 6 by 3, 2. Every group of prime order is cyclic, and every cyclic group is abelian. So this factor group G by H is abelian, but S3 is non-abelian. So converse is not true. It is possible that factor group is abelian, but group is not abelian. Next, factor group of a cyclic group is cyclic. Converse need not be true. Same example will work. G equal to S3, H is equals to identity 1, 2, 3, 1, 3, 2. So G by H is cyclic because it is of prime order, but this group G is not cyclic. Can you tell me why this group G is not cyclic?
It is not abelian also. साइक्लिक का abelian होते हैं ना.
वैसे ठीक है कि cyclic implies abelian. So not abelian implies not cyclic. बट अगर साइक्लिक की जनरल डेफिनेशन जो मैंने समझाई है उसके अकॉर्डिंगली सोचो तो
जनरेट उसमें ये फिर इसमें जनरेटर से देखना पड़ेगा या फिर इसका जो ऑर्डर है, ऑर्डर ऑफ द एलिमेंट इज द ऑर्डर ऑफ द ग्रुप चेक करके से उससे चेक करना
तो सिंपल सा लॉजिक है. इसके पास 3 सिंबल्स होते हैं ना 1 2 3 S3 के पास. तो S3 has order 6 but there does not exist any element of order 6 in S3. That's why it is not cyclic. Next theorem. let G be a group and let ZG be the center of G if G by ZG is cyclic, then G is abelian. G is a group, ZG is the center of G, G by ZG is cyclic. Cyclic implies abelian, so G by ZG is abelian. So G is equals to ZG. ZG being center is abelian, so G is also abelian. Next, consequences of the theorem. ये जितने भी मैं रिजल्ट्स बता रही हूँ ना हर क्लास में, इनको ध्यान रखना ज़रूरी है, फिर वो क्वेश्चन में ना कनेक्ट होती जाती हैं 3-4 चीज़ें. रिजल्ट्स याद होंगे तब कनेक्ट कर पाओगे, अदरवाइज मुश्किल आ जाती है. If G is non-abelian, then G by ZG is not cyclic. Second, if G is a non-abelian group, of order PQ such that P and Q are prime, then ZG is equals to identity. If G is a non-abelian group of order PQ such that P and Q are prime, then center of G will be identity. Third, if G is a non-abelian group of order PQ where P is a prime and center of G is not equal to identity, then order of center of G is P. If G is a non-abelian group whose order is PQ and center is not equal to identity, then order of center of G is P. Consider the group G is equals to Q by Z where Q and Z are the group of rational numbers and integers respectively. Let n be a positive integer then is there a cyclic subgroup of order n, A part not necessarily, B part, yes, a unique one. C part, yes, but not necessarily a unique one. D part, never.
जो इसका फैक्टर ग्रुप बनेगा उसके एलिमेंट्स ऐसे आएंगे p बाई क्यू प्लस जेड। तो इसमें फिर ऑर्डर तो 1 ही हुआ, क्योंकि अगेन अगर मैं p बाई क्यू प्लस 2 जेड लेती हूँ तो वो तो उसमें एब्जॉर्ब हो जाएगा ना 1 जेड वाले में।
ऑर्डर वन नहीं होगा।
इसके एलिमेंट्स को कैसे लिखेंगे? ऐसे लिखेंगे ना p बाई क्यू प्लस जेड।
इसी तरीके से लिखेंगे।
सो p बाई क्यू प्लस जेड, p बाई क्यू प्लस 2 जेड। नहीं, पर ये तो जेड ही है ना, तो एक p बाई क्यू और p बाई क्यू प्लस जेड कर ले, 0 लेंगे और तो 2 आएगा फिर ऑर्डर।
डिस्कस कर लेते हैं।
हाँ, ये लिखना नहीं आता मुझे।
सो q बाय z is equals to a upon b plus z, where a upon b belongs to rational numbers. Now let n be a positive integer. Then h is equals to 1 upon n plus z. This will be a subgroup of q by z, which is cyclic of order n. Because in the question we are asked, is there a cyclic subgroup of order n? So we are able to find a cyclic subgroup of order n. This is a cyclic subgroup of this q by z vector group. So for any positive integer n, there always exists a cyclic subgroup of order n So that's why A part is wrong and D part is also wrong, because A part was saying not necessarily and D part was never. So A and D part are discarded. Now I need to check that whether this subgroup H is unique or not. So let H1 is equals to A by B plus Z be another cyclic subgroup of order n. This means that order of A by B plus Z, this is n. So this is n because A by B plus Z plus A by B plus Z up to n times. This is equal to Z. This is n times. And what is the identity of H1? It is Z only.
Yes, ma'am.
Identity of H1 is Z. So A by B plus A by B, so on till A by B up to n times is equals to Z. This means that NA by B plus Z is equals to Z. Now by property of coset, A plus H is equals to H. This implies that A belongs to H. So here NA upon B, this belongs to Z. So I can write it as N is equals to Bm, where M belongs to Z. Basically it will be like this, na? Na upon B is equals to some M. So N is equals to Bm by A. So B into M dash, इस टाइप का लिख सकते हैं इसे. So A by B is equals to AM by N. From here B is N by M, na? So AM by N. So my H1 is generator A by B plus Z. So instead of A by B, I can write AM by N plus Z. So this will be like this only, 1 by N plus Z, because AM by N belongs to 1 by N plus Z. So this means that there is unique subgroup of order n. So that's why option C is wrong. So answer is option B. Next question. Consider the group homomorphism phi mapping from M to R to R given by phi A is equals to trace of A. The kernel of phi is isomorphic to which of the following groups? A part M to R by A belongs to M to R such that phi A is equals to 0. So this is basically a factor group only. B part R square, C part R cube, D part GL to R.
ऑप्शन ए।
नो,
इसमें कर्नल जैसे डिफाइन करते हैं ना कि आइडेंटिटी ऑफ कोडोमेन, कोडोमेन की आइडेंटिटी तो आर है, 0 होगी ना। तो
कर्नल
ट्रेस ऑफ ए, ट्रेस ऑफ ए शुड बी इक्वल टू 0। सो अच्छा, not to get the trace of M2R। M2R जनरलाइज लीनियर ग्रुप तो होता है, फिर डिटर्मिनेंट 1, ये डिटर्मिनेंट नॉट इक्वल टू 0।
किसका?
जनरलाइज लीनियर।
अच्छा, जनरलाइज लीनियर ग्रुप का।
हाँ, determinant not equal to 0. So here we have trace of A equal to 0, no? This isomorphism को भी चलता नहीं होगा। तो फिर ये M2R या तो फिर R स्क्वायर होगा, इसमें GL2R भी नहीं हो सकता।
नहीं, दोनों ही नहीं होंगे। ट्रेस ऑफ A is equals to 0 means
matrix equal to M2R है तो दो आयन वैल्यूज होंगी, तो λ1 plus λ2।
matrix will be like this ना, A B C minus A of this type. Its trace is 0. What is the dimension of kernel phi then?
Dimension will be just a minute. See. 3 kernel 3.
3. Now tell me, kernel phi will be isomorphic to?
एक कंडीशन जाएगी ना इसमें।
These are 4 options. Which option has dimension 3?
Sorry, C or D?
C part na? C part.
C part.
Dimension is 3 na?
Dimension is 3.
Because dimension of R cube over R is also 3. So answer is C part, R cube. Next, let G be a group with order of G as 96. Suppose H and K are subgroups of G with order of H is equals to 12 and order of K is equals to 16. Then A part, H intersection K is equals to identity. B part, H intersection K is not equal to identity. C part, H intersection K is abelian. D part, H intersection K is not abelian.
C part, abelian.
C part is correct. It is MSQ. More than one option is correct.
Okay. Order right, but two. A and C.
नहीं.
फिर तो एक ऑप्शन है A and B. नहीं सॉरी B and C.
B and C.
आइडेंटिटी नहीं होगा, इसके लिए चेक करना पड़ेगा. नॉट इक्वल टू आइडेंटिटी कैसे चेक करेंगे?
ऑर्डर ऑफ ग्रुप G is 96. पहले abelian बता रही हूँ, उसके बाद बताती हूँ कि आइडेंटिटी क्यों नहीं होगा. So H, order of H is 12, order of K is 16. So H intersection K is a subgroup of H also and K also. So this means that order of H intersection K divides order of H, and order of H intersection K divides order of K also. This means order of H intersection K divides order of H, which is 12, and it divides order of K, which is 16. So order of H intersection K can be 1, 2 or 4. These are the only possibilities. Which satisfy above relation. So H intersection K is always abelian group, because we know that every group of prime order is cyclic and hence abelian. Every group of order p square is also abelian, because group of order p and p square, where p is a prime, are always abelian. So option C is correct and option D is wrong. Now I need to check whether H intersection K is identity or not. This means that I will check whether order of H intersection K can be 1 or not. So if order of H intersection K is 1, then we know this formula na, order of HK is equals to order of H into order of K divided by order of H intersection K. So this means that order of HK is equals to order of H into order of K, which is 12 into 16, and order of H intersection K is 1. So 12 into 16, this will be greater than 96 na? Because order of group G was given as 96. Is it possible?
No, ma'am.
It is not possible. This means that H intersection K cannot be identity, which is absurd, as H is a subgroup of G, K is a subgroup of G. This implies HK is a subgroup of G. So order of HK is less than equal to 96. So order of H intersection K cannot be 1. This means that H intersection K is not identity. So option A is wrong, option B is correct. So answer is option B, C. अब यहाँ पे ये फॉर्मूला याद होना जरूरी था. अदरवाइज मुश्किल आएगी।
यस।
ठीक है, ये जो भी फॉर्मूलाज हम डिस्कस करते हैं ना, इनको एक जगह शॉर्ट नोट्स बनाते जाओ और उन्हें देखते जाओ।
हाँ, वो स्टार्ट कर दिया मैंने अभी। डीई से स्टार्ट किया हुआ है, फिर डीई के बाद 1 बाय 1 करते जा रही हूँ।
क्योंकि ये कई बार डायरेक्ट फॉर्मूलाज या थोड़े बहुत रिजल्ट से ही क्वेश्चन हो जाता है। How many proper subgroups does the group Z direct sum Z have? 1, 2, 3, infinitely many.
इनफाइनाइटली में नहीं होगा, बिकॉज यहाँ पे तो हम एलसीएम लेते हैं ना, तो जेड भी इनफाइनाइट है और ये भी जेड है।
वो बात तो ठीक है, बट सब ग्रुप्स जेड के किस टाइप के होते हैं?
इसके तो हम ऐसे ले लेते हैं ना, लाइक 0, 1 और या 2 के मल्टीपल्स या 3 के मल्टीपल्स, 4 के मल्टीपल्स, एन जेड कर ले सकते हैं सब
ग्रुप्स ऑफ जेड are of the type nz where n belongs to natural numbers. So subgroups of z direct sum z are of the form nz direct sum z and z direct sum nz where n belongs to natural numbers. So there are infinitely many. Answer is option D. Now next concept. One second. Silo's theorem. First thing, we will study conjugacy classes. This is very important concept. Silo's theorem is also very important. Let G be a group A comma B belongs to G are said to be conjugates if there exists G belongs to group G such that B is equals to GA G inverse. Now conjugacy class of A, it will be denoted by class A and it will be given as GA G inverse such that G belongs to G. So conjugacy class is given by this conjugates. Now conjugacy is an equivalence relation on G. How it is an equivalence relation? Let us check this. First is reflexive. A is related to A for all A belongs to G, as A is equals to EA E inverse. By this I will get A again. Second thing, symmetric. Let A be related to B. This implies there exists G belongs to group G such that B is equals to GA G inverse. Now if I pre-multiply by G inverse and post multiply by G on both sides, we will get G inverse BG. This is equal to A. So A can be written as G inverse B, G inverse inverse. So B is related to A. Next is transitive. Let A be related to B and B be related to C. This implies there exists G comma H belongs to group G such that B is equals to GA G inverse, C is equals to HB H inverse. So C can be written as H and B is GA G inverse, H inverse. So this will be HG A G inverse H inverse. G inverse H inverse can be written as HG whole inverse. So A is related to C. Now this equivalence relation gives rise to the equivalence classes called the conjugacy classes. Conjugacy classes partition the group into disjoint classes. So by this equivalence relation we will get equivalence classes and these are known as conjugacy classes, and conjugacy classes will partition the group into disjoint classes. If A belongs to center of G, then class of A will be singleton A only. Now let us discuss some examples. First, D4. This is equal to 1 R square R cube, S SR square SR cube. Now class of 1. This is singleton 1 only. Class of R. This will be R cube. Class of R cube. Class of R square will be separate, R square only. Class of S. It will contain SR square. This will be class of SR square. Class of SR. This will be SR cube. This is class of SR cube. Next, D5. 1 R square R cube, R to the power 4, SR square, SR cube, SR to the power 4. Class of 1, singleton 1 only. Class of R cube. This will be the same as class of R cube. Class of R square, R to the power 4. This will be same as class of R to the power 4. Class of S. This will be SR square, SR cube, SR to the power 4 for dihedral group Dn. If n is odd, every reflection comes under the same conjugacy class. Here n is equals to 5. This is odd. R denotes rotation. S denotes reflection. That's why n was odd. So every reflection comes under only one conjugacy class. Next, number of conjugates of A belongs to G. If G is a finite group, then the number of conjugates to A. This is given by order of class of A. This is equal to index of G is to class of A, where this is CA. G is to CA, where CA is the centralizer of A in G. Next is a very important concept, the class equation. Let G be a finite group and G1, G2 so on till GR be the representations of distinct conjugacy classes of G and not contained in the center then order of G is represented by order of center of G plus summation I equal to 1 to R. Index of G is to CGI, centralizer of GI. Now, two of the most important applications of the class equation. Class equation topic is also important. I think जून 2023 एग्जाम में क्वेश्चन आया था, मतलब ऑल्टरनेट एग्जाम्स में इसका क्वेश्चन आता रहता है और इजी क्वेश्चन आता है, टफ नहीं आता ज़्यादा. Two of the most important applications of the class equation. First, any group of prime power order has a non-trivial center. Means if any group has prime power order, then its center is non-trivial. Zg is not equal to identity. If order of G is equals to p to the power alpha, p is prime, alpha is greater than equal to 1, then order of center of G is greater than 1. Second, any group of order p square is abelian. Next, Sylow's theorem. This gives the partial converse for the Lagrange's theorem. Do you know what is Lagrange's theorem?
पहले की थी एक बार, ये पर याद नहीं है. Lagrange's तो divisor subgroup, the order of subgroup divides the order of group.
Order of subgroup divides order of group. Sylow's first theorem. Let G be a finite group and P be a prime such that P to the power K divides order of G and P to the power K plus 1 does not divides order of G. Then G has at least one subgroup of order P to the power K called the Sylow P subgroup. So Sylow's first theorem states that G is a finite group and P is a prime such that P to the power K divides order of G and P to the power K plus 1 divides order of G. Then G has at least one subgroup of order P to the power K and it is called the silo P subgroup. Next, Silo's second theorem. Let G be a finite group H be a subgroup of G such that order of H is equals to P to the power alpha. Then H is contained in some silo P subgroup of G. Moreover, two silo P subgroups are conjugates. G is a finite group, H is a subgroup of G such that order of G is equals to P to the power alpha. Then H is contained in some silo P subgroup of G and also two silo P subgroups are conjugates.